Hi, everybody. Dr. White here with a little coda to our discussion of exponential and gamma random variables. So just what would you do to compute the probabilities for them if you needed to in R? So here I am on RStudio, and I've got this old file that I probably don't need up anymore, so I'll X it out. And I'll go into the common folder /com Dr. White's stuff, Math331, scripts, and there's a Ch03-2.r, which I will open. And I'll go file, oops, that's not what I wanted. File, save as, and I'll ... to point back Twiddle's home. Okay, and double click my notes and just save it right in there. Alrighty, and so this is also going to cover uniform random variables from section 3.1. So like if you wanted to work with a uniform random variable, then the appropriate family of R functions is Unif, with little letters in front of Unif. And the parameters are called min and max, not A and B. So like imagine that X has a uniform distribution on the interval 5 to 10. If you needed values of the PDF, I mean, you scarcely ever would, you would use DUnif. So like, what's the value of the PDF at 7.325? Well, I know what it is. I mean, it's got to be 1 over the width of the interval, 1 over the 5 units from 2 to 10. So this had better turn out to be 0.2. Let me run it and look in the console, and yes, it is. On the other hand, the value outside the interval for the probability density function is 0. So the DUnif at 11.3 should return 0, and yes, it does. So at least it's working. The CDF, if you needed that, like if you needed the chance that capital X is less than or equal to 8.3, then you're into the P type of function, PUnif. 8.3, specify the min and the max, off you go, 66% chance. Of course, the CDF formula is just so easy to apply, upper minus lower over the width of the total interval, and you get the same thing. What you'll probably do more often is randomly generate, unifs from some interval. So if I wanted to randomly pick from the interval 0 to 10 100 times, I'd do RUnif 100 for how many times I want to do it, specify my min and my max. And off we go, and you'll see these numbers are all between 0 and 10, and they look pretty scattered around. How do you deal with exponential random variables? So in the book, they tend to focus on the theta parameter. We're going to tend to focus on the rate parameter, the lambda. And the lambda parameter in R is called a rate. That's the parameter that you use. So for our example, let's let capital X be exponential, where the rate lambda is 2. So if you need the PDF, it's DEXP, whatever X value you want the height of the PDF at, and you got to say rate equals 2. And so there it is. Now that's not a probability, that's just the height of the density curve. Here's the height of the density curve at 3, and you'll see it's a lot lower, which makes sense. Remember, the graph for these functions is exponential with a negative power, so it's like going down to the x-axis really fast. The bigger the x is, the much smaller the PDF ought to be. As for the CDF, you use PEXP. So let's think about the fact that for an exponential, the median of the distribution is theta times the natural log of 2. Okay. So like if we were to ask for the probability that the random variable is less than or equal to theta times the log of 2, that should turn out to be 0.5, half the area being before the median. So let's go ahead and ask just to check ourselves. So you do PEXP, and then you got to do your theta, which is 1 over the rate, so 1/2, times the natural log of 2, and the way you do that in R is with log. That gives you the natural log. Log of 2, your rate is a 2, and sure enough, 0.5. What if you needed to simulate some situation, where there's a random variable that's exponential? Then you use REXP. And here I am getting 1,000 random exponentials where the rate is 2 every time. And I'm storing the results in a variable called sims that you now see in the global environment. It's a little vector of 10,000 waiting times until first event. And the expected value of an exponential is the theta, right? So here the theta is 1 over 2. So the average of trying your random variable a lot of times should be pretty close to 1/2. Let's take the mean of all those sims, and sure enough, it's going to be around 0.5. Your results are going to vary from what I've got in the console because we haven't set a random seed to keep them all the same. As for gammas, alpha and your rate, you actually, the alpha parameter is called a shape parameter in R, okay? And so let's set something up. Let's let X be the time to wait for the 4th event in a Poisson process where the events occur half an hour apart on average, so that the theta is a 0.5. So the rate of the process would be 1 over 0.5, which is 2 per hour on average, same rate we've been working with. What's the chance that you got to wait more than 3 hours? Well, you could use the P gamma to get the chance of less than or equal to 3 hours, but you got to specify your alpha and your rate. Now, the alpha is called a shape parameter. We'll see why in a little bit. And the lambda parameter, is still called a rate, like in exponentials. So 1 minus this is what you need. About a 15% chance that you'd have to wait more than 3 hours. If you need to work with chi-square random variables, there's a chisq family, CHISQ. So like the probability that a chi-square with 5 degrees of freedom works out to less than or equal to 4, just piece chi-squared, 4 df equal 5. 45% chance. Hey, let's just generate a bunch of chi-square tries. A bunch of tries of a chi-square random variable where the degrees of freedom is 5. How about 10,000 of them? So you can do that with R chi-square. 10,000 df is 5. And what I'm doing here is I'm going to construct a little data frame where there's only one column, and it's called X. And it's those 10,000 random values. And that data frame shall be called df, not degrees of freedom, sorry, data frame. And so I make it, and here it is in the global environment. And if I click on it, I can see that one column, kind of like in an Excel spreadsheet. Okay, now you can send a data frame into the ggplot function that makes graphs for us. So again, you don't get interested in the details unless you've already taken Computer Science 115. But if you do ggplot with this data frame, where you aesthetically map the X position to the X variable in that data frame, and you ask for your geom, your glyph, to be a density curve with the color underneath the curve being any color you like. How about burley wood? And if you also ask for a rug of individual values at the bottom, then you're going to get a nice graph. I need to library ggplot2 to make sure that package is attached, and then I can run this function. And I'm going to get this nice little graph here that I'll get my face out of the way. And so a density curve is we're not going to discuss at the moment like exactly how the computer makes them, but it's an attempt to say, it's an attempt to make the best guess it can at what the PDF for the random variable would look like based on the data that it's got for the random variable. So based on these 10,000 tries, it constructs that curve. And it does indeed look like one of the chi-square curves as I've advertised them. So you can try that out. You can try out like different values for degrees of freedom. Like how about degrees of freedom is 1? And try it again. And you get something that looks more like some kind of exponential distribution. Who knows, it might even be an exponential distribution. How about degrees of freedom 2? Okay, and let's try that out. And that's still, it looks like it might not be a hump, actually. It might still be kind of like an exponential distribution. Let's try degrees of freedom 3. And I'm definitely getting, looks like humps now. Let's try degrees of freedom 7. Yeah, no doubt about it. Kind of one hump, but it's still got some right skew to it. What if we tried like degrees of freedom, I don't know, 50? Huh. So it's a one hump, but you know, there's a lot less left right skew now. It looks like it's sort of getting to be symmetric and even kind of bell-shaped. What if I had degrees of freedom like, I don't know, 1,000? Kaboom! It's like looks completely symmetric and kind of bell-shaped. Interestingly, also, the mean is at 1,000, and you know, you might wonder why that happens, but if you think about it, you can, because chi-square is a special case of gamma, you already know formulas for the expected value of chi-square. You can work it out, and it turns out it would be 1,000. It turns out the expected value of a chi-square is always its degrees of freedom. Well, anyway, these kinds of explorations make us think, hey, let's head to the app and look at some of these random variables. So let's use dist explore from the BCSCR package. So run that command. And I'll get rid of my face again. And let's head to, hey, maybe gamma. So the way I've got it set up at the moment is that the alpha, the shape parameter, is 3. So the random variables, you're waiting for the third event to occur in a Poisson process where the rate is 0.2 events per unit time. So 5 units of time on average between events. And why don't we just bump up the shape, you know? So I'll just put my focus here, and then I'll use the right arrow to get 4, 5, 6, 7, and 8. And I don't know if you see this, but I kind of see that the skewness is kind of going away, and that one hump is looking more and more like a bell shape. Let me go ahead and drag the number of events you're waiting for all the way up to 100, and wow, that looks like a totally bell-shaped curve, you know? Let me put it back down to 3 again. Okay. And let's play with the rate. So right now it's at 0.2, but let's like drag it up to, you know, here's 0.6 events per unit time. Here's like 1.21 events per unit time. And like 1.82. Wow. You know, I'm changing the rate. And so I'm changing actually what the numbers here are on the x-axis because I'm really dealing with different random variables each time. But the shape is still the very same as when the rate was back at, you know, the 0.2 that we began. Yeah. So changing the rate parameter does not affect the shape of the distribution. It only like moves it to the left and right along I guess along an axis, but it really doesn't have an important effect. Well, I guess it does kind of squeeze and compress as well, but the basic shape, the basic skewness is unaffected by changing the rate. What affects the skewness and makes things look more or less bell-shaped is changing the alpha. And that's why the alpha is called a shape parameter in R. You can get similar benefit by looking at the exponential distribution. And I don't even bother to show a chi-square here because it's a special case of a gamma. Okay, guess we'll just close out of the app, close the window, click the little red stop sign, and I feel like I'm just ready to log off. And we'll see you later.